Hi guys, in this lesson we will talk about NURBS curves, what they are, how Alias and other CAD systems construct them, what's the difference between NURBS and B-splines, if any, what knot vectors, spans and basis functions are, and how all of this works together. As you probably guessed from the preview, it's going to be a theory-heavy lesson, but don't worry, it won't be a math class. Now, I already raised a similar topic in my lesson called spans, which was about spans and knot vectors. And while the content there was legit, I think I did a poor job of explaining what spans really are. And this is because I gave you pretty specific information without context. And that context is the concept of NURBS curves and how CAD systems use them. So I'm gonna try again and give you all the necessary information to make the picture complete. I don't know how many of you are into this kind of stuff, and if heavy theory is not your thing, that's fine. You do you. Just skip this one. I personally believe it's important for any industrial designer, but you may think otherwise, and that is legit. Okay. So buckle up and let's start by creating a curve in Alias as our reference point and switch to my scribbles that we will run through together. So I will be switching back and forth between the Alias and the scribbles. So I will create for this lesson a curve. I will create a parabola. So I'll open up my CV curve tool and I will use 3 degrees with uniform knot spacing. We will tackle this. This is pretty important. And by the way, this value, the uniform, is set by default, so you don't need to switch anything. And I will just create a parabola. Okay, so this thing is a NURBS curve. And as you're gonna see, Alias constructed it just using points I provided Alias to work with. So the only thing Alias knows is the positions of these points, and it was able to construct this NURBS curve using only these 3 points. Now, to understand the NURBS curves and what the spans are and all the other nuances of NURBS modeling, we need to figure out how it actually happens under the hood and how Alias and other CAD systems do that. So let me switch to my scribbles and I will go through all of this. Now there's quite a few, but trust me, once again, this is not a math class, it's more for the illustration. We will not calculate anything ourselves, just to understand the general logic. So NURBS. NURBS stands for non-uniform rational B-splines. And this is a very important naming. Every single phrase matters here, and we will understand what all of this means and what the NURBS means when we go step by step in how CAD systems actually create them, and through that understand what all of this really means, all of this non-uniform and what is rational and what is B-spline. So here you see the kind of somewhat a depiction at what we have in Alias. So we have a curve which constructed for 3 points, Q0, Q1, and Q2. Now here, as you're going to see, I have their coordinates in Cartesian coordinate space, X and Y. Now I used in the example in Alias and here just a planar curve. It can be not planar in 3D, doesn't matter, just for simplicity. So we have X and Y, we don't have Z, or better say Z is 0. So what will happen underneath the hood in Alias? So first, you set your CVs, and we already did it in Alias. So we add 3 points, and Alias constructs a curve. So we provided Alias with these 3 points. So Q0, Q1, and Q3. Every single one of them has its own coordinates in Cartesian space, as I said, X and Y. So X0, Y0, X1, Y1, X2, Y2. This is, well, basically everything we need to provide with Alias. Everything else it will do automatically. So next, Alias will calculate a degree. So the degree is a derivative of polynomial, or amount of derivatives of a polynomial. Now, how it calculates it? It calculates it very simply. It calculates the quantity of the points, and we introduced 3 points to Alias, and it is subtract 1. So 3 points, 3 minus 1 equal 2. So the degree of the curve will be 2, or basically it will have 2 derivatives of a polynomial. Now let me just go back here, and if you look at the control panel, you're going to see I add 3 control vertices and the degree is set to 2. Now I didn't do that, Alias does it automatically for me. So let me go back. So in general, and I probably mentioned before that underneath the NURBS curves there is a complex polynomials and a lot of math behind them, and it is true. But there is a nuance. So right now, when we talk about the degree or derivative of a polynomial, Alias will take in mind that this is a 2 degree curve, and we have 3 control vertices, which means that the polynomial itself will have 2 derivatives, and the 2 derivative polynomial will look like this: ax squared plus bx plus c. It's probably something you vaguely remember from your math classes, parabolas, and you actually made a parabola, and a parabola can be described by this polynomial, but not directly. And this is very important. Even though that we're talking about the polynomials, Alias actually doesn't use them directly. So it's just for the show. So at the end of the day, Alias knows the amount of points. We have 3 points. Alias knows the degree and amount of derivatives, which is equal to 2. What will happen next? Next, Alias will create a vector knots. Now, in math papers, they're actually called knot vectors, not the way around. But I called it vector knots because, for me, it just, sound more pleasant to my ears, vector knots. But of course, this is not vectors. We're talking about the vectors, of course. So the knot vectors described by the range of numbers. Now, right now, it's for you, of course, it's a pure abstraction, but let's just start with calculating the vector knots and then describe what they actually are. So the calculation of the vector knots is very simple. You add the quantity of your points, which you add, and we know that we used 3 points. So 3 points plus the degree, and the Alias already knows the degree. The degree is 2 derivatives, plus 1. So 3 plus 2 plus 1 equals 6. So that means that our vector knot will consist with 6 numbers. And here there is a abstract example. I'm not saying that it's exactly like that. It may be like that. It really depends on the knot spacing, and I will tackle that a little bit later, actually at the end of the video. But there is 6 numbers. So there is number 1, number 2, 3, 4, 5, and 6. You're going to see 0, 1, 2, 3, 5, 6. So this is the 6 numbers. Now, what the vector knots actually do? Well, they define how, I already mentioned actually here. So it defines how the t parameter spreads along a curve, uniform or not. Now, to understand this, first of all, what is t parameter? Now, t parameter, it's in math papers. In computer graphics, it also has, in NURBS geometry, it's called u. So this is a u parameter or a u direction. The surfaces, the NURBS surfaces has 2-dimensional domain, u and v. The curves has 1-dimensional domain, u. What is this domain? What is u? Well, this is actually the t parameter. So we know that for 3 CVs and 2 degrees, we will have a vector knot with 6 values, and the 6 values will define how the t parameter will spread along the curve. So uniformly or not. Now, before we go into the actual t parameters, let's figure out what does it mean uniform or not. Now, these vector knot defined only by 2 values actually. So the distinct values, there is the value 0 and the value 1. It repeats itself, and that's for a reason. We will talk about it in a sec. But what's more importantly, that there is only 2 values, 0 and 1. That means that the t parameter will be somewhere within the domain from like, I'm sorry, I'm just I don't have space for my Cintiq, so because I have a microphone in front of me, so I will try to do it with a mouse. So the from 0 to 1, there will be parameters, and these parameters are within. Now, how many of them we will discuss a little bit later, but there is something within it from 0 to 1, and these notes that it spreads along the curve uniform or not means that in this example, for example, this t parameter will spread uniformly from 0 to 1 without any stops. For example, 0, 0.2, 0.4, 0. And so on and so forth until the 1. But on top of that, these spread can be non-uniform. And now we go back to the original naming and we will look at this. It said non-uniform rational B-spline. Now we don't know what the rational B-splines are, but now we can look at the non-uniform and figure out, okay, so the way how the t parameter spreads uniformly or non-uniformly actually defines what the NURBS are. Now this uniformity, or the lack of it, describes the amount of spans. So the vector knots actually tied very, strictly speaking, straight to the spans. Now here, in this vector knot, it basically says that there is only one span, and the span goes from 0 to 1. Now, if we look here, when I describe a little bit what the spans are, the spans calculates extremely simply amount of control vertices minus degree. And we already know the amount of control vertices. Alias already calculates as the degree, so amount of derivatives. So what we do is just subtract one from another. 3 minus 2 equal 1. One span. So this vector knot defines one span from 0 to 1. Now you still don't know what the t parameter is, but you're going to see that it will be a one span. So every single time when you add a span manually or automatically, Alias do it for you, Alias automatically adds additional CV. So every new span means that the new control vertex will be created. So we started with 3, but if you want more than one span, we need to increase the amount of control vertices, and Alias does it automatically, and any other CAD system will does it automatically. So just in abstraction for now, the two spans will be 3 CVs plus 1 equal 4 CVs. This is exactly what I explain in a second. And our vector knots will change. So remember, it was from 0 to 1, one span. Here, it will go from 0 to some intermediate value to 1. And now we have, as you're going to see, 3 distinct values within our vector knot. Now, before we have only 0s and 1s, now we have 0, 0.5, and 2. That means that the span separates this domain, these vector knots, like 50-50. So the span actually are not these values, these ones. They are not spans. The spans are in the middle. So this is the space between the parameters. And as you're gonna see, we have 3 values, which means we have 2 spans. Now, right now, the spans are just still an abstraction. So yeah, we have these vector knots, which defined by the amount of the derivatives and the amount of control vertices, and then we can add additional control vertices with existing ones to increase the amount of spans. Now, we still don't know what the spans are, right? So before we move on, we need to quickly figure out another concept. This is the concept of edit points. Now, these numbers, unique numbers like 0, 1, and 2, they actually represents in the interface of Alias. Rarely in other systems. It's mostly in the surface modeling tools when you really need a lot of control. Other tools like Rhinoceros or especially like more modularized CAD software systems like, I don't know, FreeCAD, for example, they don't do that. Or maybe, I don't know, Moi 3D. So these edit points, they marks these values on your curve. Now, you don't really know how yet, but if we open up my example, let me just, duplicate this in Alias, and I will increase the amount of spans. Now, first of all, as I said, additional control vertex, control vertex will add. So 0, 1, 2, 3, 4. Here was 3, now it is 4. So one control vertex was add to the overall domain. And here, if I zoom in, you're going to notice that there is this additional elements. Now, for you, it's probably not the case. If this is the default state of the alias for you, then in the display draw style, it probably set to something like this. So it's kind of not existent here. It's a very, very tiny small dot. So I will just increase it for this lesson so it will be easier to see, so they will not overlap. So there is 3 values in our domain now, distinct values, 0, 0.5, and 1. And on these distinct values, the edit points placed. So the first one is in the beginning, the next one is at 0.5, and the next one at 1. So 3 edit points. Let's go back. So now this is the edit points, and I actually visualize that the edit point equals the vector node. So every vector node here, I already described, this is 0, this is 1, this is 2, and they are just right there. Now, before we move on, we need to and talk a little bit more about the t parameter and why we really need this and why we need spans. We need to address this issue with repeated values, right? So we have 0, 0, 0, and 1, 1, 1. Why we need 3 in the beginning and 3 in the end? Now, the vector node defines how the t parameter will spread, and we want that our curve, when we construct the curve, it starts specifically at the beginning, at the first control vertex, and ends at the last control vertex, right? So we don't want the situation where we create a curve and then we create a point and then another point and another point, but instead of starting from the first point, it starts starting somewhere else, right? It will be very strange. So we need to force the curve starts drawing specifically from the origin, from the first control vertex which we add in Alias. And these repetitive values actually they actually does exactly that. So why 3 numbers? Why not 2? Why not 10? Now that's because as I said, at the core of all of that, there is of course a polynomial, and the derivative defines how fluid the curve will be, how much it can bend, the amount of torsion it may have, its fluidity. So to force curve starts from the point 0, we need to be sure that the derivatives are equal, they are the same, and at the given point. So the amount of repetitive values refers, or it's in a very specific relationship with the amount of degrees of your curve. And the relationship is very simple. I won't really deep dive into explanation why it is the case, but the amount of degrees plus 1 equals the amount of repetitive elements in the beginning and the end of the vector node. So we have 2 degrees. 2 degrees plus 1 will equal 3. It means that we will have 3 values at the beginning and 3 values at the end. And as we already know how many values will be in the vector node, because it calculates by the amount of control vertices plus the degree plus 1, we know that it will be 6, so it all works in correlation with each other. So 3 to the left, 3 to the right. In contrary, if the amount of the degrees will be different, amount of repetitive elements of the vector node to the left and to the right will be different as well, by the very basic arithmetics which I described. So now we briefly understand that the edit points are marking the specific values of the vector node on a curve, and we figure out that spans are breaks in the vector node as a whole. So how many chunks in the vector node are there? Now, for now, of course, it's more like an abstraction, as I mentioned before, because we didn't really ground it yet. So as we're going, from top to bottom, how Alias constructed, I will explain it a little bit later. So the next step, when Alias figure out how many spans will be there and what is the vector node, how the vector node looks like, And let's assume that we are actually working with a single span surface. For now, we will tackle the two spans a little bit later. So imagine that we will toss this one down. So next, what will happen is the spread of a t-value, or the t-parameter. Now, I already mentioned that the vector node defines how the t value, or the u parameter, if you will spread along a curve. But we don't have a curve yet. At this point, we just have only numbers. So this t parameter is the already confined by the domain of the vector node. So the vector node starts from 0 in where's my cursor? Holy shit. Come on. Okay, here it is. I'm sorry, I just have 3 monitors and it just accidentally switched to another one. So the vector node defines the domain, so beginning and the end. So the t value will be somewhere between 0 and 1. But how many of them will be there? Well, that's what Alias defines automatically based on your tolerances. So your document in Alias has tolerance, the specific tolerance with which everything is constructed, how tight your tolerances are, tolerances for curvature, tolerances for tangency, how accurate the curve will follow your commands, and how accurately it flows through the control points, and so on and so forth. And even though that we don't have a very specific value in Alias and its construction options, which will define how much we're supposed to spread, Alias does it itself under the hood. So, and it spreads a lot. So for the domain between 0 and 1, it can spread a lot of t-values. For example, something between 0 and 1, 0, 0.001, 0.002, or maybe 0, 0.00001, 0.0002, and so on and so forth. There is a bunch of them, a huge list of data. So I mentioned here in the top that the vector nodes defines how t-parameter spreads along the curve, uniformly or not. But this spread doesn't mean that it really defines where it is on the curve. No, it just defines, is it, spread of chunks, or it just a one big sweeping list of data. And when you have spans, which basically splits the domain of these t values on two parts, so from 0 to 0.5 and from 2.5 to 1, which means there is two spans, it means that there will be two big lists of t parameters, t values. The one big chunk goes from 0 to 0.5, and another one goes from 0.5 to 1. Simple as that. Now, what will happen next? Now, once again, at this point, we didn't construct anything. We just consumed and rearranged information, get additional information. We started just with 3 points with XYZ coordinates, and now we have the amount of degrees. We have our vector node, which defines the chunks, how many chunks we have of the t values. We already have the list of t values. There can be a bunch of them. What will happen next? Next, we're still not constructing the curve. Next, we define we calculate the basis function. Now, the basis function is the core. This is the meat of NURBS curves as well as the B-splines. It's what makes everything happen. Now, the basis functions for degree 2 and depends on the derivatives of the polynomial, how complex it is, and we already figured out how Alias calculates what is the degree of the curve. It will create the specific amount of basis functions. So the basis function, the way how they really looks and how many of them defines by the degree and the amount of control vertices. So this formula was proposed a long time ago by Edwin Cox and Carl de Boer. I believe it was somewhere in the 1950s or something like that, far before anyone was born and before the computers as we know today. So it was pure abstraction. And this formula then fleshed out. And through this formula, the concept of NURBS as a mathematical concept was born. So what it does, now the basis function, and I'll go through that in a second, but in general, the basis function and the purpose of the basis function is to define the control vertices voice. So it defines the loudness of the voice of every given control vertex which you introduce to Alias along the curve. So every single one of them has a voice. And I say voice casually. This is not the official term. It's just I made it up. But I believe it just kind of serves the purpose really well. Now, to understand what it does, let me just kind of quickly, draw a curve here. Now, imagine that this is the point number 1, which we introduced. This is like somewhere the point number 2, and this is the point number 3. Now, every single one of them has voice, as if it, shouts like, hey, curve, come to me. And the next one say, no, come to me. And this one goes, no, you need to go towards me. And every one of them has this voice. What's more important here, and that's what basis function does, is that it can calculate the loudness of the voice depends on how far you are from the point. So for example, you are somewhere here, right? Somewhere here. Let's just call it shit. Like somewhere here. And at this point, the further you're away from the control vertex, the dimmer the sound. Like, in real life, if you, shout at the person, he's far away, you need to shout loud, otherwise it will not hear you. But the closer you are to the person, then the louder your voice will be, if you don't tone it down. So this is the same. The further you're away from the control vertex, the dimmer the sound of this one, but become to be more prominent this one. If you are here, or maybe even here, then this one is in full effect. You hear it really well, and this one are dimmer and dimmer. And that's what basis function does. It defines a value which at every given point on the curve which we will construct will calculate this loudness for all control vertices. So here we have 3 basis functions. This is the basis function 1, this is the basis function 2, and the basis function 3. Why we have 3 basis functions? We have 3 basis functions because this is a degree 2 polynomial, so we have 2 derivatives, and because we have 3 points. So the basis function will calculate for every control vertex it has. So if you have 3 control vertices, we will have 3 basis functions. And if the degree will be bigger, then the basis functions will be slightly different. So they're not. This is the example for 2 degree. Now, once again, it's based on the Edwin Cox and Carl de Boer formula. It's pretty complex, pretty intricate, and very beautiful, to be honest. If you're interested, you can Google it and get into the papers and figure it out yourself. This is just a very condensed example, practical example, a practical/abstract example. So here in the formula, you're gonna see that this is the t parameter. What is the t parameter? Well, we already know this is the values which we know the range of. So it starts from somewhere to somewhere, how many chunks it has, 1 span, 1 big list, 2 spans, 2 different lists, 3 spans, 3 different lists with the beginning and the end, and within there is a lot of these t values. So once again, I'm now just talking about just a single span, so it simplifies things a little bit. So it will take the t value, which Alias spread, I don't know how many, a lot, and it plugs this t value, the t parameter, for control vertex 1, then for control vertex 2, and for control vertex. And here I made a mistake. I already see the n0. This is the value for control vertex 0, the first one. This is for the control vertex 1, which is the second one, and this one's supposed to be 2, of course, so not 3, 2. So 0, 1, 2, 3 control vertices. And as a result of this formula, we get a huge list of t values, like as many values as Alias gives us with this t parameter. It's just kind of like a huge list of values, and they separated by 3 control vertices. So the control vertex 0 has a lot of values for the t parameter, and then the q1 it has a lot, and so on and so forth. So every single one has a bunch. Now these t parameters eventually will define the points on a curve. So these t values, they right now they are abstract, but they slowly starting to give shape So they work in relationship with the control vertices, and these values, these t values, then eventually become to be our coordinates. For now, they are not. So for now, we have the point number 1 and all the list, the t values, the different values for all the parameters. Now, I'm really plugging it into the curve, but for now, they're just a list, right? And it has different values. And then we take the second one, this is the second control vertex, and it goes again for all the same ones over and over again. But the values are different. You know, this one has the bigger value, this one is the smaller, and vice versa. The third one, all the CV values, but this one is the bigger and this one is the lower, right? So it goes through all of them for 3 points. And this is how it get this relative voice loudness. So based on how far you're away from one control vertex to another control vertex at a given t parameter. Right. So what will happen next? So we have already a lot of stuff. Once again, we have control vertices, which are our coordinates x, y, z. We have amount of control vertices. We have a derivative, the amount of derivatives for our curve. We know that this is 2. We know the vector knots. We know these vector knots are uniform or non-uniform, right? So does it have spans or not? In my example, it will have no spans, so just a one big chunk. And we have the basis functions, the loudness, the relative loudness for every given control vertex at a parameter. So parameter for every given control vertex. What will happen next? And the next, and this is the step 6, is that where Alias actually constructs the curve. Once again, when I say Alias, I mean all CAD systems. Just example of Alias, but it's true, it's universal. So what will happen is that at any parameter t, once again, we still get the same parameters t, we plug that here, right? And then we will take the original ones, which we plugged here, and take them again. So we take these t values again, but this time we will calculate the actual coordinates, x and y coordinates of every given parameter for our curve. So it will form us the chain of points for which Alias will connect and construct a curve. So the qt here is the actual x and y values for every given t parameter. And it calculates very simply. You take the your result of the basis function. Once again, the basis function was already calculated at the specific parameter. So we take that and we multiply it by the coordinates of our control vertex. So every given t will go through this. So the basis function for the control vertex number 1 multiplied by its coordinates plus the basis function for the so this is control vertex 1, this is the control vertex 2, or better say 0, 1, 2. The next one with its calculated basis function, and then the next one, and then the next one, and then the next one. So as you can see, everything adds up here. So we take all the big data which we have and then eventually kind of plug it all together. And everything is tied to the basis function, the t parameter, and our control vertex coordinates. Because without coordinates, we actually can't construct, you know, other points. That's where the magic happens. So these qt, or x and y coordinates, will be calculated using this formula for every given parameter. And that's how we get our points, and that's how Alias interpolates for this point and give you this beautiful NURBS curve, in our case, a parabola. Now, one important note here is that this formula, and I call it B-spline. I'm not calling it NURBS. Why so? Now, there is no error here. This formula, as well as these basis functions, they are for a B-spline, not for the NURBS curve. Well, why I did that then, right? Well, there is a very interesting nuance here. You see, we actually need to get back to deep dive into actually the naming. So I said that the NURBS means a lot and the B-splines means a lot. So to understand what's going on, we actually now need to understand the second part of the naming. So non-uniform, we already figure out what the non-uniform is. It's just the domain. Is it the vector knot domain? Is it separated, or it's a one big chunk, which means it defines spans? So non-uniform, we already understand. The next one is R. R stands for rational. So non-uniform, rational B-splines. So the non-uniform rational B-splines is different from B-splines, but only in one nuance. The NURBS are rational and B-splines are non-rational. This is the only difference. The fact that this one is non-uniform and the B-splines for some reason is not is bullshit, because the B-splines are, of course, non-uniform. The NURBS are non-uniform and the B-splines are non-uniform because B-splines, of course, has spans as well, and they, of course, has vector knots and everything else. So the only difference between the NURBS and the B-splines is the NURBS are rational, or better say they can be rational, and the B-splines are always non-rational. So what is rationality means then? Now, in general, you must think, well, probably rational ties to the rational numbers, right? It's kind of is and kind of isn't. Now, of course, Alias operates only within the rational values. It doesn't operate with the rational numbers, as well as any other software. So in this regard, that's true. But what it actually refers to in the concept of NURBS is to CV weight. Now, remember that I said that we, through the basis function, we calculate a relative loudness. You know, the further away from one point, then dimmer it is, and the other one become to be louder, right? So, but I never specified the actual loudness of the CVs by default. Maybe they are silent, you know. What is the difference to calculate that if they don't have any sounds? There is supposed to be some sound for them, right? The default value for all of them. So, the CV weight, actually, I understand it's kind of like a strange term, but the CV weight, it equals to the default voice loudness, and it will be affected by the basis function, of course. So here in our basis function example, there is no CV loudness. It's not there. It's not plugged. So we have the basis function and another one, and we can find the relationship between them, which one's supposed to be louder relative to the position to other ones in the T value. But we didn't specify the actual loudness of themselves by default. And that's what the CV weight actually does. So for the NURBS curve, not the B-spline, the NURBS curves as a finalized concept, the basis functions, every single basis function, they are still the same, like literally the same, but they will be multiplied. They will be multiplied by the CV weight. So the first one will be multiplied by its CV weight, and the second one by its CV weight, and the next one by the CV weight. Now the variable called W for the CV weight. Now I don't know why, because you know the people decided. I don't know who made it. Maybe Les Beagle defined that it's supposed to be W. Actually, I don't know. So it's not important. What's important here, and that's why I actually use the B-spline to explain everything here, how Alias constructed, because it is actually what happens under the hood. Because in Alias and in any other CAD system, W set to 1. But if the W is set to 1, so the standard loudness is set to 1, which is actually very common in math in general, in geometry, in trigonometry, it's set to 1. That means that it has no effect. If you multiply something on 1, you will get something, it will not change. And because of that, in the situations where, the default situations where the voice is set to 1, nothing will change, which means that it doesn't matter, do you use the basis functions for the NURBS or you use the basis functions for the B-splines, your result will not change. And in this case, the B-spline and the NURBS are identical. They give you literally the same result. That means that when you, work in Alias and you do like your curve stuff and you create your curves, mathematically speaking, you're working with the NURBS, but because the W is 1, strictly speaking, this is a B-spline. So, the NURBS is it's a mascot for the CAD modeling, right? It's become to be a mascot for the CAD modeling, but it doesn't necessarily means that you use NURBS at full potential, because by default the W is 1. Why it is 1? Well, there is a lot of reasons why it is 1 by default, why Alias keep it 1. Some of the systems actually, even though they call themselves NURBS modeling tools, they actually always set it to 1 and never give you the ability to change that. Basically, effectively transforming NURBS to just a standard B-splines. Now, there is a reasons for that. And the reasons why Alias use 1 by default, why ICM use 1 by default, and other CAD systems who have this value use 1 by default. And that's because when you use the power of a NURBS at full potential and you actually spread the different weights, default weights or default loudness for every given value, the result may exceed your expectations. So NURBS are just additional construction over the standard B-splines, and this is very situational. And the only situation where you actually need NURBS at full potential when the Alias using additional math. I will not be diving into this, it's not really that important. It's interesting, by the way. I encourage you to deep dive if you're really looking for this, but in our case, let's just pretend that there is some algorithm which automatically can define the default loudness for every control vertex. Now, of course, Alias and other CAD systems need to know the algorithm, and the algorithm based on the specific, let's say, very specific math, and it works only specifically designed to operate with conics. Conics means the revolves, profiles, and circles, right? So if you create a circle, if you create revolve in Alias or in ICM, for example, then you may go into the settings and say, I want that my NURBS will be real NURBS. And Alias understand, as well as the ICM, for example, that you are creating the circle because you use the tool called circle, and it's like, okay, I know you want to create a circle, you asked me to be rational, so I will go in, use additional algorithm, and I will tweak the default loudness of every single CV weight. So instead of like default 1, it will be something else. Now, once again, I will not be diving into the actual nuances of this one. That's not important. What is important, this exception exists. And if we go back in Alias just a bit, and I will go to the construction options right there, scroll down. Here you have this checkbox, rational flags. And if you watch my videos about the circles, you're already familiar with this. If not, that's okay. So rational flags, I have two checkboxes, primitives, curves, and surfaces. And for now, right now, every single curve here, mathematically speaking, it is a NURBS, it's not a B-spline because it has weight. And if I will open, you're going to see the weight 1. Remember what I said? W1. So the weight is 1. And this one is 1. And this one is 1. And this one is 1 again. All of them will be 1. And that's because it effectively transforms them to just the standard B-splines. And if I will create, let's say, a circle, so let me create a circle here, and I will select any point in our circle, you're going to see that they all are 1. Once again, I specify that I want to have a circle, and it's a conic, but I not specified that I want to have rationality. If I will click on the rational flags and I would like to say, hey, I want it to be rational, then when you create a circle next time, and I will select these CVs, you're going to see their weights are now fluctuating. This one is 0.9, and this one is 0.84, and this one is 0.82, and this one is 1, and so on and so forth. So Alias automatically, it knows that you want to, that the form, to create the proper form, to create it ideal, to create the perfect radii, just the B-splines are not enough. You need this additional tweak for the weights to really create the perfect radii. And in fact, if I will take the radius here, you're going to see that it's literally spot on. That's because we are under the rational flags, because this circle constructed through the NURBS curve at full potential. This one is a NURBS curve too, but the weight is 1, which means that you will get your fluctuation. So this is 0. This is 858, and this is 879. This is 8. So as you can see, it's fluctuating a little bit. Now it's pretty accurate, of course, but you're going to see that the fluctuation happens. So that's not ideal. And that's where the power of the NURBS actually, visible. It's in the conics. In all other aspects, just the regular B-splines will be just fine. Or at least when we're talking about the curve creations. But of course, underneath, mathematically speaking, you are really operating with the NURBS, not with B-splines. It's just the value of W is 1. So let's go back in my scribblers. So as a conclusion for the for the NURBS curves, but it's not final yet, I would like to address the polynomials. Now I already addressed it before, and I said that the polynomials are within the core of NURBS geometry. And even though that here, as you're going to see, there is no polynomials whatsoever, we use basis functions instead. We use vector knots. Where is the polynomial? Well, there is none. And that's because polynomials, they are not used directly. So we know the formula for creating the polynomial with basically any complexity. So this one, for example, is the polynomial in the degree of 2. It describes parabola ax squared plus bx plus c. We can increase the degree, and it will be ax in the power of 3 plus bx squared plus x plus d, and so on and so forth. And we can make this list increasingly complex to infinity. The problem is that the a, b, c, d, e, and other variables, the more complex your polynomial, the more derivatives it will have, the more values you will have. They are coefficients, and these coefficients, a, b, c, and so on and so forth, they defined by vector knots and basis functions. If you don't have vector knots and you don't have these basis functions at the math concept, you will not be able to construct a curve based on polynomial. So polynomials can be used to analyze already created curve, but constructed straight from the polynomial, you can't. That's why, smart people designed the concept of NURBS, and that's why the basis functions appears with these voices and the CB weights and vector knots. It is a really smart workaround to create something from nothing, from a very, very limited amount of data, construct yourself a beautiful curve. And it's really beautiful, really. If you deep dive into that, you will realize that it's a simple, in some ways extremely complex, but very beautiful concept. And that's why it's with us till this day and will work for years to come. So now that's not over though. Now I promise we are really close to an end. Just a little bit of your time. I will go back to the top, and now I would like to talk a little bit more about vector knots. Now you already know that the vector knots designed to define the space of the T parameter. Is it a uniform space or non-uniform space? Which means that the vector knots defines spans. You have 1 span, 2 spans, 10 spans, million, gazillion spans, or whatever spans. And even though that I didn't say it, but I believe now, after we get to the very end with the calculations, you now, I believe you know already and understand it, but if not, just quick recap. The spans which we have here, they define the T parameter, which we use in all the basis function calculations in the final assembly separately. So if you have one big chunk, it will be calculated to one big sweeping curve. If we have 2 chunks, it will be 2 different basis functions, the 2 different assemblies stuck together. So they still share the same properties. They are the part of the one big thing, but they described by 2, 3, 5, 6, 7 more different chunks. And these chunks are stuck together. And the spans, the beauty of the spans, and the reason why we have these spans, why we in the first place use this non-uniform approach, is because really complex basis functions, and the basis functions based on polynomials, if you have a very, 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 very complex polynomial with a lot of control vertices, I don't know, 100 million, let's say 100, it's already crazy. So if you have 100 control vertices, right, you have a really big, the amount of derivatives, in real life, in real practicing examples, the Alias works with a specific tolerance. Alias rounds the values as well as any other computer. So the fluctuations of the complex polynomial, the more and more complex it becomes, is very difficult to control. So you will have this unwanted torsion, and the more the control vertices you bring, the more and more of them affect at the same time on the curve. So it will become to be almost impossible to accurately construct the curves without any hiccups, dimples, sudden torsions and stuff like that. That's why Alias and other CAD systems, they limit the amount of derivatives you can work at the time. So the maximum for Alias, I believe, is 9, right? I believe it's 9. Yeah, it is 9. And I believe ICM, if I remember correctly, if I recall, it is 12. But 9 is already overkill. It's already, if you need 9, you probably did something wrong. If you need 12, then oh my god, you definitely did something wrong. So this is an overkill. It's already difficult to control, and that's why if you really have a long curve with a lot of torsion and bend, these spans that basically defines the vector knots on chunks and process them separately give you ability to maintain this beautiful complex curve, and at the same time limit the fluctuations within the span itself. So this is like a limited ability of control. It can confine within the piece. Now, of course, they are continuous within each other. Remember, this is the part of the general vector knot, the big vector knot. That's why they still maintain the continuity, but their changes within are localized, and that give you an ability to create a really complex, controllable curves. Now, in Alias and in other CAD systems, in A-class surfacing modeling, you probably heard it before from me and from other people that in A-class we prefer working with single span surfaces. There are a lot of reasons to that, but even though that spans, if there is a lot of spans, they can actually add discrepancy on the on the edit points, these vector values, because if it will be really, really cramped, there is just not a lead-in, not enough scale for the tangency and continuity to spread itself too much. It can be very confined, and that's why you get these kind of small irregularities in the surface. And to battle that, you basically separate it on different chunks and work with them as a single independent, absolutely independent pieces. But to get to the situation, you actually need to construct the bigger curve or the bigger structure first, and that's where the spans are very handy. On top of it, of course, there is parametric modeling, which works with spans. Without the spans, it'll be absolutely impossible. So spans are useful in one way or another in A-class surfacing, even though that to some extent we try to get rid of them, but at the beginning they're always there, and we actually need them to construct the proper shapes and then define them and tweak them as we like. So the spans defines these different sections. So now I hope it's pretty clear. But of course there is one more thing, and now we go back again to the vector knots, and I would like to close with the vector knots, and because there is one more important thing to mention. So there is two types of vector knots. There is uniform vector knots and there is chord vector knots. And these vector knots, these uniform or chord methods defines how vector knots will be spread along the domain of the curve, where they will be. Now, if I will open up the Alias again and I will create the curve, you're gonna see, so once again, there is a knot spacing, the chord and uniform. Now, I don't like the naming, but this time this is not Alias' fault. I mentioned multiple times that I don't like Alias naming convention, but this time this is not Alias' fault. This is just from the papers. And this chord and uniform describes the mathematics, but it doesn't describe the reasoning. Why, what's going on? Now, by default, Alias always has uniform spacing turned on by default for all of the tools and for the curves as well. So it is uniform. Chord is an option. And if you don't touch it, that's fine, but at least you have an option. So what's the difference? So when we define at the point 3, when we Alias creates the vector nodes, and we know how many vector nodes we need to have, so how many elements will be, and we know how to do it. We know that in our example for parabola it is 6, and we have a single span. The type of the vector node doesn't matter. So it always will be between 0 and 1. It always will be the same. But when you add additional separations using spans, basically using transforming the vector node from a uniform to non-uniform, when there is really specific chunks, then the uniform and chord defined how these chunks will be presented in the vector node, and because of that, they will define where these edit points, where the beginning and the end of every span will be placed on a curve when the curve will be constructed, through which curve will be constructed, better say. So all of the vector nodes can be either normalized or non-normalized. By default, Alias doesn't normalize anything. So if it is within 0 and 1, that's great. If it's bigger, not a big deal. Alias doesn't care about that, but it cares about spacing. So the uniform is the top one. This is the example for the uniform. That means that every new vector node, every new edit point, better say, so here, every new edit point, because we have more than one span, they will be parameterized in the vector node by an integer. So if the first one, the beginning is 0, and you have non-uniform span, non-uniform vector node, for example, you have 2 spans, that means that the next one will be 1. And the last one will be 2. So you have 3 edit points, 0, 1, 2, and 2 spans in between. And this is what you see here, 0, 1, 2. Alternatively, in the chord vector nodes, if you use this spacing, the chord nodes, the next one, the next value, so the first one will be 0. The next one will be calculated by the chordal, the chordal length. So it basically every next edit point, every next separation will be like a cumulative sum of chordal lengths, and the chordal length is the length between one edit point and another edit point. Now, if in the uniform we are talking specifically and only about internal parameterization, we are not talking about any actual distances. We are not tied to coordinates on anything. It just uniformly increase 0, 1, 2, 3, 4, 5, 6, 7. It is within the parametric space of your domain. The chord instead, it actually constructed. Now, if the curve is not constructed, or it is constructed, you want to change it, the algorithm of calculating the chord will be slightly different. It either use approximations based on the control points, or it use existing edit points. It's a different story. It's a really complex topic on itself. We don't really dive into it. The only important thing here is every next value for the edit point in your domain will be defined by the chordal length. So for example, this one will be divided by the chordal length, and this one will be divided by its chordal length plus the previous one. So it can be 0, and then it can be 3, and the next one can be 135, and second will be 1 million gazillion. What it means is that the curve actually become to be parameterized. So these values, like 0, 2, 35, 37, they're not just numbers in the vector node, which will be squashed into the parametric space uniformly. This is the actual lengths of your curve and where the edit point is supposed to go. This is geometric. So we actually spreading the values on the domain based on the actual distances. If we don't have the spans at the beginning, we have the curves, it approximates using, as I said, the control vertices, or vice versa. Once again, there is a lot of ifs. But the overall result is that the distances of these values, where basically the intervals of the spans will be defined by the actual distances, or the chordal lengths of the edit points. What does this mean in practice? That means that the uniform parameterization or the uniform node spacing doesn't mean that in practice all the CVs, all the edit points will be uniform. But what it means is that it will be uniform in the parameterization space. For example, let me show you. So in Alias, if I let me just delete this, and I will create. Let me just delete this, and I will create a curve. So I will go into the curve, and I will use uniform, and I will create the curve somewhat like a parabola, not exactly, through these points. Now here I have four spans, and if you look closer at this curve, you're gonna see that let me just I can't isolate it. Okay, so you're gonna see that this is the span number 1, and this is the span number 2, this is 3, and this is 4, and we have 1, 2, 3, 4, 5 edit points. We already discussed edit points. So the reason why this CV is here and not here, and this one is here and not there, or vice versa, is because of a uniform distribution of the vector nodes. It distributed along the domain uniformly. So the distances in the domain from, like, for example, from 0 to 1, like 0, then the next, like, you know, like if there is 3.0, 0.51, right, or 0, 0.25, 0.5, 0.751. In parametric space, they are absolutely uniform. But in practice, of course, that means that as the surface, you know, the curve is not straight, right? It bends. It means that whereas more acceleration, right, the CVs will be closer to each other. The further you from acceleration, the more linear it is, the less spacing. So the more spacing between the spans will be. So visually, it's not uniform, but in the parametric space, it is. That means that if we, for example, let's say create a surface from this, and we will divide it by isoparms, they will be very uniform, because the surface domain and the surface constructed the way that it forms the inner parametric structure of UNV coordinates. Alternatively, when we're talking about the geometric or chordal length, when it just calculates the chordals, let me just do it again, and I will activate the chord this time, and I will go from first, second, third, and we just keep going the same stuff here. Already you're going to see that there is a difference. There is a difference. Look, this one was uniform and this one was chordal, and you're going to see that it shifted quite significantly. And it's not only shift the positions or basically the lengths of the spans, it changes the curve. So the curves are now slightly different. And that's because that when you use chord and you use these distances, the real distances, the actual spread of the spans, more in line with the actual geometry. It kind of holds the actual geometry a little better. It works with tandem with the geometry you want to do. Your curve will be curvier. Your sweeping lines will be a little bit sweepier. That's not like a big difference, but there is a difference. Why then the Alias use uniform by default? Well, there is a few reasons for that. Even though that ideally, as geometric, spread of vector nodes is more in line with the actual geometry you want to do, instead of just dividing parametric space on equal values, it comes at a cost. And there is a few. Well, first of all, it's become to be quite difficult to adjust and align them. So for example, you want to keep continuity between one piece and another piece. And because of the curvature, right, the way how the edit points spread to follow the geometry, it accommodates the geometry, but at the same time, the values may be floating, and it's really difficult to the distances between the edit points at the point of connection can be too short or too long, and it will be difficult to maintain curvature if you want to align it to something else. In uniform, this is not the case. Another big problem with chordal is that Chordal butchers your internal structure. So in the uniform parameterization, if you create a revolve, a surface, something, and you divide it by the UNV directions to create some parametric pattern on top using Grasshopper and a Dynamo, you will have no issues. But if you have chordal instead, this spread will be non-uniform anymore. The curve will be great, but the surface from that may be the grade as well, but it will be really difficult to uniformly place something on top of that. Apart of that, there can be some issues with the texturing, but there's not a lot of people who do texturing work, so in this regard, it's not important. Now, in 99.999%, everybody use uniform. There is a few exceptions for automotive industry where sometimes you really need chordal, but it's extremely rare. In my practice, I never encountered it myself. I know that some other people do. I didn't. And in general, for professional, for casual, it doesn't matter where you work. Even if you're working for automotive, chances you will be working with chordal are very slim. They may be, but rarely. So when you create the curve, be sure that you are in a uniform, and it will eliminate some pain when you will try to adjust two curves together, and these curves are multi-span. And one important note, this chord and uniform, they only true when you have non-uniform vector node. So if the vector node is uniform, so there is only one span, it doesn't matter which one you pick. It will work identically. It will make differences only when you have more than one span. And that's I believe important to mention. Right. So I believe this is everything you really need to know about the NURBS curves. And of course, this is not everything. That's the concept is deeper than that. But I believe now you understand how that works. So, as a conclusion, B-splines are a subset. Let's put it this way: it is a subset of the NURBS mathematical model, which, as it stands today, is a global standard for CAD modeling. The construction of NURBS curves defined by CVs, basis functions, knot vectors, and weights is consistent. It is consistent across all CAD systems, not only Alias. And these, let's say, global standard, it gives us designers an ability to create everything from smooth automotive surfaces to intricate freeform shapes, and understanding the core principle of NURBS, whether it's the predictable uniformity of edit points or the principle of trade-off between complexity and control with spans. Let's say it equips you with the intuition to craft high quality designs where navigating navigating the mathematical rabbit hole with let's say let's be shy with relative confidence. And on top of that, NURBS are beautiful if complex concepts. So learning it just a little deeper than the average Joe pays respect to the giants like Edwin Cox, Carl de Boer, Les Beagle, and many others who made all of this possible for us. And and on this note, thank you for watching, and I will see you in the next one.